I'm going to try to graph some Limacons. So Limacons are anything in the form of r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. There's 4 different kinds of Limacons. I'm going to start with one where the a and the b are the same. We don't really worry about the sign of it, whether it's a plus or minus. That will just affect where the long part of the diagram goes. Is it going to be on the positive x, positive y, negative x, or negative y? We'll see how that goes a little bit later. Because these are going to be the same, we don't really have to know the name of it in advance to graph it, but it'll kind of evolve as we do this. But you are going to have to know the names of the 4 different kinds of Limacons. This one's going to be what we're going to call a cardioid. So it should hopefully, if I do this right, look like a heart when I'm all finished. So for all of the Limacons, what I'm going to do is I'm going to plot points. So I'm going to find out what is r equal to when theta equals 0. I'm going to then find out what is r equal to when theta is pi over 2. And then I'm going to find out what r is equal to when theta is pi. And finally, when theta is 3 pi over 2, we'll solve for the r, and then we're going to plot those points on an axis. So when theta is 0, sine of 0 is 0, so 2 times 0 is 0. We're just going to get r equals 2. So I'm going to plot this on, let's see, an xy axis. So I'm going to put the axis in white over here, and then I'm going to go on theta equals 0, which is this angle right here. I'm going to go out a length of 2, and I'm going to plot that point there. Now, we label points here in rectangular coordinates. In this case, that the polar and the rectangular would be the same. So we could think of that as a positive 2x and a 0 for y. It's also a positive 2 for r and a theta equals 0, but that's the only time those are going to match. I'm going to come back over here now to theta equals pi over 2. Sine of pi over 2 is 1. 2 times 1 is 2, plus the other 2 makes r equal to 4. So here is our angle pi over 2. If I come out from the pole a distance of 4, that's going to put me right there. I'm going to label that in xy coordinates as 0, 4. So there's a second point on our curve. At theta equals pi, sine of pi is again 0. 2 times 0 is 0, plus the 2 makes r equal to 2 again. Here's our angle pi. If I come out on that 2 from the pole, that's going to give me that point right there. I'm going to label that in rectangular coordinates, xy coordinates, as negative 2, 0. And finally, at theta equals 3 pi over 2, sine of 3 pi over 2 is negative 1. Negative 1 times 2 is negative 2, plus 2 gives us r equal to 0. So that is going to put us, whoops, I accidentally erased my axis. Let me redraw it. And so that's going to put us right at the pole or the origin, and so that's the point 0, 0. Now when we go to connect these, then I'm going to start here at that original point. As I kind of sweep using Doppler radar, as I go through, I'm trying to figure out how to show these, as I go through these different angles, working my way to pi over 2, then I'm going to connect these points there, and the r values are going to get just gradually bigger, and I'm just going to connect it with a nice smooth curve. Likewise, when I then go from pi over 2 to pi, then I'm going through these various different angles here, and I'm going to connect these as I go along there. The r values are going to go from 4 back down to 2. Down here in quadrant 3, these angles are going from pi, gradually working their way towards 3 pi over 2, and the r values are going from 2 to 0. They're going to make a curve that comes all the way in to the origin or the pole. And likewise, going quadrant 4, from 3 pi over 2, going over towards back to 2 pi, which is the same as 0, we're going to get our curve there. And so we can see it kind of looks like an upside down heart, and that's why we'll call that a cardioid. So a cardioid is going to be when the A and the B are equal to each other. So when that A and that B are the same, doesn't matter what the signs are, just if in absolute value the A and the B are the same. Okay, I'm going to go get a new screen here, and I'll do a different kind of rose curve here. So I'm going to start with R is equal to, let's say, 2 minus 3 cosine theta. So we'll get a look at a different cardioid, because in this case our B is bigger than the A. I'm not worried at this point about the negative sign, but the 3 is going to be bigger than the 2. That's going to lead to a different cardioid. I'm going to start, as I always do, I'm a different limacon, I'm sorry, not necessarily a cardioid. This is a different limacon. So I'm going to put in theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2, and I'm going to graph those as we go. So the R on the first one, when we put in 0 for theta, cosine of 0 is 1, times negative 3 is negative 3, 2 minus 3 is negative 1, the R is going to be negative 1. So on the angle 0, the negative means I go through the pole to the other side, and it's going to put me over here at negative 1, 0 is going to be the coordinates of that point. It's kind of a weird way to do that with polars. How you do the negative value of R, you go on that angle, but you shoot through the pole on the other side of the origin. At pi over 2, cosine pi over 2 is 0, so R is going to be 2. So at the angle pi over 2, I'm going to go up 2, and I will label that in xy coordinates as 0, 2. At pi, cosine of pi is negative 1, times the negative 3 makes that positive 3, plus the 2 is going to give us an R value of 5. So on the angle pi, which is over here, I'm going to count out from the pole 1, 2, 3, 4, 5, and plot that point, and in rectangular coordinates, that's going to be negative 5, 0. At 3 pi over 2, cosine is again 0, and so we'll just get 2. So at the angle 3 pi over 2, we're going to come out from the pole 2, and I'll label that in rectangular coordinates as 0, negative 2. Now, graphing this is kind of strange. We're starting now, thinking this kind of as Doppler radar. I'm just going to start here at the first point, which is at negative 1, 0. Now, as the angle goes this way, and originally, now the very first R value is negative, which put us on the left side of the origin. As we work through these angles here, as we're sweeping up towards pi over 2, then originally these angles are still going to be negative values for R, which is going to give me points down in quadrant 3. At some point, I've got to go through 0 on my way to getting to a positive 2. So that curve is going to do something like that, where it's going to come through the pole and end up over there at 0, 2. Then as I continue sweeping from pi over 2 to pi, now the R values are going from a positive 2 to a positive 4, so they're just going to get bigger. And I'm going to try to do that with a curve. That didn't look all that great, but something like that. As we sweep then from pi to 3 pi over 2, the R values are going to go from 4 back to 2. So we're going to try to connect that with a curve. Now as we go from 3 pi over 2 to 2 pi, again, we're going to connect this point that's at a positive value of 2 for R back to where we started, because 2 pi is the same as 0, back to that negative 1, means the R value's got to go through 0 somewhere on its way to a negative 1. And so we get this, it's called a looped limacon. That's one way you can say it, is a looped limacone, or you can also call it a limacone with an inner loop. Limacone with an inner loop. And so that's what we get when our A value, or when our B value is bigger than the A value. That's going to get us a looped limacone. Okay, I'm going to do another one, so I'm going to get a new page. So here's going to be now our third limacone. This time I'm going to say R is equal to, and let's do 3 minus 2 sine theta. So in this case, the A is bigger than the B. So we'll get something that looks a little bit different. So I'm going to again start by finding the values for theta, as we always do with limacones. So I'm going to, let me erase that. That's going to be pi, and then theta will be 3 pi over 2. So I'll make my axis over here so we can plot it as we go. And when we plug in 0 for theta, sine of 0 is 0, so we'll just get r is 3. So I'm going to go 1, 2, 3. There's our point, and I'll label that in xy coordinates as 3, 0. At pi over 2, sine is 1, so negative 2 times 1 is negative 2, plus that 3 is going to give us an r value of 1. So at the angle pi over 2, I'm going to go 1 away from the pole, and I'll call that 0, 1. At pi, sine is back to 0, and so r is going to be 3 again. Here's our angle pi, so if I go 3 out from the pole, I'm going to label that in xy coordinates as negative 3, 0. And at 3 pi over 2, sine is going to be negative 1. The negative 1 times negative 2 is positive 2, plus 3 gives us an r value of 5. So at the angle 3 pi over 2, I'm going to go 1, 2, 3, 4, 5. Let me extend that axis a little bit more. And so here is going to be our point, and I'll label that 0, negative 5. Now, I'm going to graph these, so I'm going to get a green dot. Here's where we're going to start. I'm going to connect that to this point, but these numbers are going to be a little bit bigger, and they're going to end up kind of dipping down, not to a sharp point, but kind of to a rounded valley right there at 0, 1. And then I'm going to connect it to that next one, so they're going to start to get further away as I make my way over here. And then as we go from pi to 3 pi over 2, we'll go from 3 away from the pole to 5 away, and then going back to where we started, we're going to get this curve. So you can see that this point, this area right in here, kind of like a cardioid, it starts its way back towards the pole, but different than a cardioid because these will never actually equal each other. It never quite reaches the pole, and it doesn't have then that sharp point to it. And so this is called either a dented limacone, or it can also be called a dimpled limacone. So it starts in towards the pole, but it never actually reaches the pole. Okay, so there's our third limacone, and I got one more to do, so I'm going to get a new page for that one. And we'll say here r is equal to, let's say, 5 plus 2 cosine theta. So in this case, our A is more than 2 times the B. And so these, I think, are the most boring of all of those limacones, but that's just my personal opinion. We're going to do as we always do with limacones. We're going to plot the points on the quadrants. So see what we're going to get for r at 0, pi over 2, pi, and 3 pi over 2. So at 0, cosine of 0 is 1. 1 times 2 is 2. 2 plus 5 gives us 7. Let me get an xy axis up here. So here is going to be my xy axis. Let me see if I can erase that. And so at theta equals 0, I'm going to be out here at 7. 1, 2, 3, 4, 5, 6, 7, and that's the 0.70. At pi over 2, cosine is 0. So 2 times 0 is 0, plus 5 gives us an r value of 5. At pi over 2, we'll go 1, 2, 3, 4, 5, and that's going to be the 0.05. At pi, cosine is negative 1. 2 times negative 1 is negative 2, plus 5 is going to be 3. So at the angle pi, oops, let me get that back. At the angle pi, I'm going to go 1, 2, 3, and call that point -3, 0. And at 3 pi over 2, cosine is back to being 0 again, and r is back to being 5 again. So here's our angle 3 pi over 2. 1, 2, 3, 4, 5. I'm going to call that 0, 5. Now, this, like I said, I think is kind of boring. It doesn't have the interesting thing even that the dimpled limacon does. So it never comes in. I'm just going to connect these and get something that kind of looks like a big egg. So it never goes in towards the pole, and we don't, even though mine looks pretty wobbly there, it doesn't have that dimpled or dented part like we saw with the dimpled limacon. It doesn't even start in towards the pole. Everything is still pushed out, and this is called a convex limacon. And this again happens when the A is bigger than 2 times B. So that's it for limacons. I hope this helps make things more clear.